All right, so this is the part 2 to the section 4.2/4.3 videos, and I'm still covering concepts, so I'm gonna just continue right where I left off. So the main points from the previous video, or part 1, was that we tried to find the area under the curve for f of x equals x squared on the interval 0 to 2. So the idea is we can approximate the area using rectangles. So at first we tried using two rectangles of equal width or equal base, and we based our two rectangles on using either the left endpoints or right endpoints of each subinterval. And we got this. Using the left endpoints, we got the area of adding the two rectangles to be 1, and then using the right endpoints, like 1 and 2, plugging that in, 2x squared to get the heights of the rectangles, to get the area of adding the two rectangles to get 5. So we found a bound, or bounds, for the area under the curve to be between 1 and 5. Then we tried 4 rectangles, and again using equal width. And these are the 4 subintervals. And then we get the bounds to be 1.75 and 3.75. And so you could compare that with the 1 to 5, we get a more narrow range of values where a real area can be bounded between. So the more rectangles used, the better the approximation. In fact, using an infinite amount of rectangles gives the actual area. And that can be expressed using this limit. All right, and this video, I'll go more into the sum part of this limit. So it's the limit as n goes to infinity from I equals 1 to n of the sum of f of ci times delta x. Now the sum portion is called a Riemann sum. Delta x is the width of the rectangles, and their delta x is going to always, for our purposes for this course, we're using equal width. F and then of ci is the height of the ith rectangle. And then that notation, sigma notation, and you takes the sum, and you start with I equals 1, and you end with I equals n. So you're summing up n amount of rectangles as far as the area of the rectangles, and we know area of a rectangle is base times height, where our base is delta x, and the heights of each individual rectangle is f of ci. Okay, and we get our individual rectangles by, at least from what we've done so far, just choosing the left endpoints or right endpoints of subintervals. All right, so for our recurring example, f of x equals x squared on 0 to 2, using the 4 rectangles of equal width, we form these 4 subintervals. In general, for any interval a to b, we can form n rectangles of equal width by doing delta x equals b minus a over n. So in our case, a is 0, b is 2, and we want n equals 4 rectangles. So the width would be 2 minus 0 over 4, which gives you a half. So delta x is 1/2. And then for our Riemann sum, you plug 4 in for n, so it goes from I equals 1 to 4, and then f of ci times delta x, and in this case, delta x is a half. All right, and then again, f of ci is the height of each rectangle for each subinterval. And ci is our choice that we use for each is our choice we use for each interval. And it can be the right endpoints, left endpoints, or it can actually be whatever you choose in each subinterval. But for our purposes, we usually have been using right endpoints and left endpoints to make our lives easier. So we have these 4 subintervals, and ci in this case goes from 1 to 4. And so our first value, c1, is 1/2, c2 is 1, we get 3/2 for c3, and c4 is 2. Then we get the heights of the rectangles by plugging these c values into the function x squared. So that's where the 1/4, the 1, 9/4, and 4 come from. So these are our heights of the 4 rectangles using the right endpoints for CI. So the Riemann sum can be expressed as follows. And so right now we got 4 in for n, 1/2 for delta x. Now part of the summation is you can factor out a constant in front of the summation. So I could pull out the 1/2 in front of the sum. So that way it makes it look easier because now we're taking the sum from 1 to 4 of just f of ci. And then ci ranges from 1 to 4, so you have f of c1, f of c2, c3, and f of c4. And then we got these 4 values up here. It would be 1/4, 1, 9/4, and 4. So we plug those in. So we f of 1/2. These are right endpoints with 1/2, 1, 3/2, and 2. Plugging them into the function gave our corresponding outputs of 1/4, 1, 9/4, and 4. So we sum up those heights, times it by 1/2. That gives 15/4 or 3.75. Now all of this right here is from the previous video. It's nothing new. It's just now I'm expressing it using the sigma or Riemann sum notation. Now in general, the Riemann sum is expressed as the following, and I've already talked about each component of the sum, but it will be important, I think, to pause the video and write this down. So for right endpoints, there's actually a formula you can use for each CI value, and it is a plus I times delta x, where delta x is the width, and delta x is b minus a over n. And then there's a formula for using left endpoints, and it's a plus I minus 1 times delta x. Generally, for examples later on in future videos, I'm going to use this one for right endpoints. It's just easier to use I times delta x instead of I minus 1 times delta x. So before I apply this back to our recurring example, I first need to address some summation formulas, and this is theorem 4.2 on page 259. So there's 4 formulas that you might want to write down. So you have these 4 things, and I give an example of each 4. The first formula is taking the sum of c, where c is a constant, and it essentially becomes c times n. So it's c times the top index value of the summation. So for this example, I have the summation of 1 to 5 of 3. 3 is the value for c, 5 is the value for n, so it becomes 3 times 5, which is 15. That's the same thing as adding 3 to itself repetitively 5 times. All right, so you could just simply do it as 3 times 5. For the second formula, so if you have just a summation of I, it turns into n times n plus 1 over 2. So for example, if I had the summation from I equals 1 to 3, in this case n is 3, it would be 3 times 3 plus 1 over 2. That's 3 times 4 is 12, divided by 2 is 6. And then this is the I squared formula. And here's an example, and I used 3 again for n. So that's what it turns into. I'm just plugging 3 in for n to the formula. And it became 3 times 3 plus 1 times 2 times 3 plus 1, which is basically 3 times 4 times 7. All of that divided by 6, which is 14. And then this is the I cubed formula. And again, I'm still just using 3 as an example for n. And this is what it becomes. So n squared is 3 squared, n plus 1 squared is 3 plus 1 squared, and then divided by 4. It's 9 times 16 over 4, so it gives you 36. All right, so I would write these summation formulas down. You might use one or two of these in examples later on in future videos. Now I'm going to apply this summation formulas along with this general information about Riemann sum to our recurring example of f of x equals x squared. So I'm going to approximate the area again, and we already know what the answer is, but I'll just show it now using Riemann sum for 4 rectangles, and I'll use the right endpoints. So I just wrote down the Riemann sum, and then delta x is b minus a over n. So we know delta x is a half because a is 0, b is 2, 2 minus 0 divided by 4, and again n is 4 because we're using 4 rectangles. Now here's where something's different. For the right endpoints, instead of just forming the 4 subintervals, you can just form a formula for the right endpoints, and that was given in ci is equal to a plus I times delta x. And then a is 0. We found delta x to be a half. So it's going to be 0 plus I times a half. So the right endpoints in general form is 1/2 times I. So the Riemann sum has f of ci. So right now I know the ci part is 1/2 I. Now I need to find f of ci. Well, the function's x squared. So you just plug the value in for x into the function. So you plug 1/2 I in for x, and that becomes 1/2 I squared. And then you square that, and that becomes 1/4 I squared. So I circled in green what we're going to plug into the Riemann sum formula. So the f of ci part, the heights of each rectangle have the form 1/4 times I squared. The width of the rectangles are delta x equals a half. So that's what I did here. It's plugged those in the corresponding spots. And that gave me 1/4 I squared. That's the f of ci part. And then times 1/2, that's the delta x part. And then we simplify this, and I'm going to be using those summation formulas. So n is 4, so that's what I put in for 4, or for n. And first thing I do is to do, what is 1/4 times a half? That's 1 over 8. So I have the sum of 1 over 8 times I squared, and you can pull a constant in front of the summation. So I factor out the 1 over 8 in front of the summation and focusing on the I squared part. So here in orange, I just wrote down the general formula for the sum of I squared. It's n times n plus 1 times 2n plus 1 divided by 6. In our case, n is 4. So it'll be 4 times 4 plus 1 times 2 times 4 plus 1. All right, so we have 1 over 8 times everything in orange. And then I basically find what's in orange, and you get that to be 30. So I have 1/8 times 30, which gives us 3.75. And that's the same sum as before. All right, that's using the right endpoints. So this is a general method of finding an area or approximating the area for some function using a Riemann sum. And most of the time I'll use right endpoints unless it tells you explicitly use left endpoints or right endpoints. And then use the number of rectangles for n. So the first thing I do is I find delta x, the width of the rectangles. After I get the width of the rectangles, then I find what the right endpoints are. And I got the right endpoints to have the form 1/2 times ci, or sorry, 1/2 times I. And I plugged those into the function x squared, and that gave me 1/4 I squared. So I circled in green those values that I plugged in, and I put them in green in the formula. It gave me 3.75. So this is the actual entire work of the problem here. And earlier I did it without doing the CI part. Let's see, where was it? Yeah, right here's where I did it. basically I was doing the same thing. Instead of having to find f of 1/2, f of 1, f of 3/2, and so forth, you have a general formula for each one of those values, and it's f of ci, or whatever ci is. All right, so that gives you more information on a general Riemann sum. The next video, I'm going to go into definite integral, and then after that, I'll go into actual examples where we find these Riemann sums and definite integrals.